So today, class, we're going to be talking about multivalent metals. Multivalent metals. What do you think that means, multivalent? Well, valent, what do you think valent means? We've been talking about what type of electrons? Valence electrons. So multivalent means there's differing numbers of valence electrons. So the multivalent metals are metals that can have or I should say just have multiple oxidation states. And you really don't need to worry about that. You'll learn all about that in grade 12 chemistry. In our practical terms, what this means is they can have differing numbers of valence electrons. So for our practical purposes, that's what it means. These metals can change the number of valence electrons when they make bonds. So, I see some of you with a perplexed look on your face. Don't worry about the why right now. That's something you're not going to really learn until grade 12 chemistry. And I can't build that foundational knowledge in you. You're just going to have to accept the fact that some metals can have different numbers of valence electrons. Now the nice thing is I'm going to tell you exactly which metals those are. So, all metals are multivalent, except for a few. So all metals are multivalent except for, well, we learned about two families that always have the same charge. What are those two families? Which family is this?
Alkali metals.
Yeah, that's your alkali metals. And what charge do your alkali metals always have? They have one valence electron, so they want to positive one. They want to lose that valence electron, right? Lose one negative, makes them positive one. So all of your alkali metals always have a plus one charge, aka they're not multivalent. So your alkali metals, and in that same train of thought, what do you think is another family of metals that are not multivalent?
Hydrogen?
Those are not metals. Those are non-metals, right?
Oh,
Alkaline earth.
The alkaline earth metals, right? Your beryllium, magnesium, calcium, strontium. So your alkaline earth metals, and what charge do they always have? Yeah, 2 plus, right? They lose 2 electrons, they're 2 valence electrons to have a 2 plus charge. So those two are not multivalent. And then we have some weird exceptions. I kind of pointed them out on your periodic tables if you watch the video online. Now, those exceptions are aluminum, which has what charge?
3.
Excellent. Right, your aluminum will always have a 3 plus charge, and zinc is another exception. Zinc will always have what charge? Maybe I didn't put that in the video. Zinc will always have a 2 plus charge, and silver will always have a 1 plus charge. Now the nice thing about those exceptions is what do you notice about their actual location on the periodic table? What is their orientation to one another? If you look, aluminum, zinc, silver, they are diagonal, right? So it's really easy to remember the exceptions because it's 3 plus aluminum, 2 plus zinc, 1 plus silver. Every other metal on the periodic table you are to be treating as multivalent. So that means everything from here all the way to your staircase, you will treat as multivalent, okay? That includes all of your lanthanides and actinides at the bottom here as well. Now let me give you an example here, and I think this example will perfectly illustrate that we're going to have to come up with some unique rules on how to deal with these compounds. So let's say you had two compounds. You had this compound, and you had this compound. Now, both of these compounds are possible, and with our current naming rules, what would you call those? Yep. Yeah, that's right. It's iron with oxygen, right? We change the name of our anion, we add I to the suffix "ide", so this is iron oxide. And this is iron oxide. But you can see a flaw already, right? When we name chemical compounds, we want to clearly be able to know the formula from said name, right? We need to be able to go from formula to name and name to formula. Do we have enough information here in the name of these compounds to be able to go to these formulas? No, right? These are two fundamentally different things. Okay, so we do not currently have enough information. How do we add that information? Well, that is going to be the stock system. Now, the benefits of creating something like this is you get to name it after yourself. The stock system was invented by Alfred Stock, of course. But the stock system is how we come up with that name that will give us enough information in order to figure out our chemical formulas. Now, with the stock system, you will be adding a Roman numeral in brackets after your cation. So after your multivalent metal, we will put in Roman numerals, we'll put in brackets Roman numerals. Now, what will these Roman numerals signify? Well, they're going to signify the charge on your multivalent metal. So the Roman numerals are going to represent the charge on your multivalent metal. Now, who here remembers their Roman numerals? Yeah, I see some. We're not going to, I expect you to know up to 10. So I'm going to write them down right now. So if this is news to you, we'll have to memorize them by the end of this unit. So one is, you probably know the first 5 for sure. That's fine. Alright, who here knew all the Roman numerals? One person. 2 people. Oh, okay, 3 people. We're good. So those are really important. You do have to memorize them because we will be using them for multivalent metal. Alright, so let's use an example here of utilizing the stock system. And I'm going to stick with the 2 examples I've written on the board. Alright, so we're going to talk now, how do we go from chemical, or how do we go from name to chemical, no, we're going to go from chemical formula to name, sorry. How we go from chemical formula to name. How do we go from chemical formula to name? Do we know the charge on our metal? Do you know the charge on iron right now just by looking at it? Some of you might. But do you know it just by looking at it? No, right? We're not sure what the charge is because it can change. It's multivalent. Now, what do we know? Do we know the charge on our anion? What do you think? Yes, we do, right? What is the charge on our anion in this case? 2 minus. So we're going to be using that in order to figure out the charge on our metal. So, since we don't know the charge on our metal, we must work backwards through the anion, right? Because we do know the charge on our anion. That's not going to change. Right? The charge is constant. So how do we do this? How do we work backwards through our anion? Well, we're going to ask some different questions than we did with binary ionic. When we were asking those questions with binary ionic, does anybody remember the 2 questions I was asking? Yeah, what is the total charge, right? The lowest common multiple. And then I said, okay, well, what was the second question?
How many?
How many, right? Lowest common multiple tells us the total charge, and then how many of each ion do I need in order to meet those total charges? Here we have how many, and we're going to be looking for the total charge. So we're going to kind of work in reverse. So step 1, you want to list the charge of your anion. And in the case of both of these, what is the charge of our anion? What is the charge of oxygen? When it forms an ionic bond, what is the charge?
2 minus.
Yeah, it's going to be 2 minus. And do we know the charge on iron right now? We don't, right? So we're just going to not put a charge as of yet. That's what we are trying to find. That's what we are trying to find. All right, so step 2. You want to ask how many of each ion is there? So how many of each ion do you have? And in the case of this compound here, how many iron ions do we have in this compound? It's not a trick question. If we look at this compound here, how many irons do we have? Yeah, we have 1. And how many oxygens?
1.
We have 1. How about in this compound here? How many irons do we have here?
2.
We have 2, and how many oxygens?
3.
We have 3. And this is where your theory becomes important. What did I tell you about ionic compounds? What about their charges? What do their charges have to do? Excellent. They have to balance, right? They have to balance out. So in knowing that, we can now work backwards to our ion. So step through our anion, sorry. So step 3, we want to calculate the total number of electrons donated / received, and this actually represents your total charge, right? So this is your total charge. So I'm going to say here total charge. You can also write down electrons donated, received. Doesn't really matter. But how many electrons does oxygen donate or receive? It receives 2 electrons. And if we only have 1 oxygen, in total, how many electrons were received? Just 2, right? So just 2. Now let's use that same train of thought working through our anion here in regards to our second compound. Each oxygen wants to receive 2 electrons. If we have 3 oxygens, in total, how many electrons were received?
6.
Excellent, 6. So in total, we carry a charge of 6 negative. Negative. So, step number 4. All right, step 4. Since charges must balance, your total donated will equal, total received will equal the total donated. I probably didn't need to write this down. So what then is going to be the total amount of electrons here that were donated? If 2 were received, how many had to be donated? 2. So that means that this is a 2 plus. How about here? If 6 were received, how many had to be donated? 6. Now, last step. Last step. You're going to determine, you will determine the charge on iron now, or determine the charge on your metal. By dividing what am I going to divide here to figure out the charge on my metal? Think about it. What am I going to divide? Yep.
The total charge by how many?
Excellent. Yep, that's it. So we're going to be dividing the total charge by how many of each ion you have. So determine charge on metal by dividing total charge by how many. So for this first chemical formula, how many irons do we have? 1. How many electrons must that iron donate? 2. So what will be the charge on this iron? Yeah, it's not a trick question, it's 2. So this iron, as a result, has a 2+ charge. Now, if we look at this example here, in total, how many electrons must be donated? 6, right, for a total 6+ charge. And how many irons must be doing that donating? 2. So, as a result of that, how many electrons does each of your irons donate? 3, which means that this iron here has a 3+ charge. Now, the last thing we need to do is we just need to write down the name of our compound. So, what is going to be the name of this compound, and what is going to be the name of this compound? Everyone's done writing down these steps? We're good. So, the name of the first one, we're going to be using our Roman numerals here. What is going to be the name of this one here? It's still iron oxide, but after the iron, we're going to add some Roman numerals in brackets. Which Roman numerals am I going to put there? Remember, those Roman numerals, they represent the charge. So those Roman numerals represent the charge. Excellent. So we're going to put a Roman numeral of 2 in those brackets. So that is iron 2 oxide. What about this one here? Yeah, that's going to be iron 3 oxide. So that is how we name multivalent metals. For many students, this is one of the hardest things we learn all year long. And as a result, we're going to do one more example problem before we talk about going from name to chemical formula. But realistically, you can probably already see name to chemical formula is super, super, super easy. You don't even need to think about the charges, right? You already know them by looking at the name. So let's do one more example. I'm going to say that you have, let's go with this one. Let's say you have V2O5. V2O5. So take a minute right now and try to figure out what the name of that compound is. Okay? Alright, so step 1. What do we need to do? What do we not know? We don't know the charge on vanadium. We don't know the charge on vanadium, right? And that's what we want to find. We don't know the charge on vanadium. Do we know the charge that oxygen takes in an ionic bond? We do. What is it? 2 negative. Right? We know oxygen's 2 negative. We don't know the charge on vanadium. That is what we're trying to figure out. What are those 2 questions that I asked? We'll start with how many and then the total charge. So, first off, how many of each of our ions are in our compound? Yeah, we have 2 vanadiums and we have 5 oxygens. But you know what? Just to really illustrate how we're working through our anion, I'm just going to write down 5 for now, just to make this really clear. So we have 5 oxygens, and how many electrons does each of our oxygens receive? 2. So in total, how many electrons were received by all those oxygens?
10.
Excellent. We're just multiplying it through, right? 2 times 5. Because if each one receives 2 and we have 5, that means there must be, in total, 10 negatives received. Now, ionic compounds, your charges always need to balance out. So if 10 were received, how many must have been donated? 10. 10 must have been donated. And if 10 were donated, and how many vanadiums do we have?
2.
We have 2 vanadium ions. What must our charge on vanadium be?
5.
Does everyone understand that? So, 5, right? 2 vanadiums, each one must donate 5 electrons in order to get the 10 total that is needed. Now, a lot of students here, they will stop here and they'll be like, it must be vanadium 10. It's only vanadium 10 if you have 1 vanadium, right? We have 2 here, so each one donates half of that. They donate 5. So then, who here thinks they have the correct name of this compound? What is it going to be? Sorry?
Bracket 5.
Yeah, so it's vanadium 5 oxide. Right, so the naming rules don't change for multivalent metals other than you must include that Roman numeral. That's the only thing that changes. We still add the suffix "ide" and we don't change the name of our cation. Okay? So now let's do the easy thing, because that's really tough, and it's probably going to take you quite a bit of practice before you feel comfortable doing these problems. But you should feel comfortable right away going from name to formula, which with binary ionic compounds is harder, because you need to think about how many valence electrons there are, and how they donate them, how they receive them, what their charges will be. But with these, it's really easy. Why is it super easy for multivalent metals? What do you know just by looking at the name?
Charge.
Yeah, you know the charge of your metal just by looking at the name. So with chemical formulas, name to chemical formulas, it is much simpler than binary ionic. So you're going to use the same steps as your binary ionic. But it's easier because the Roman numeral tells you the charge on your cation. We'll say, remember, the Roman numeral tells you the charge on your cation. Since we're using vanadium and oxygen, let's do a slightly different one. Let's say instead vanadium 4 oxide. Vanadium 4 oxide. What were those 2 questions we were asking with binary ionics? Refresh my memory again. How many?
And the charge.
And the charge. Now, that's what we were doing just with multivalence and naming them. Flip the order of those questions again. We're going back to binary ionic.
Lowest common multiple.
Yeah, total charge, lowest common multiple, and then we ask what? How many? Okay, so we're going to go back to how we figured out the chemical formula with binary ionics. So you have to realize and make that distinction in your mind that when you're going from name to chemical formula, whether it's multivalent or binary, the rules are the same. The only extra rule I've kind of added today was when we are naming multivalent metals, you must figure out the charge on your multivalent metal. All right, so step one, we need to figure out the charges here on our two ions. What is it for oxygen? We've used it a bunch today. It's going to be 2 negative. What's the charge on our vanadium? What Roman numeral is that? Which one is it? It's 4, right? It's 4. So this is vanadium 4 plus. So the Roman numeral tells you the charge on your metal. Now we're going to ask those two questions again. What is the total charge, the lowest common multiple? And as a result of that, how many of each ion do I need? So what is the lowest common multiple between those two?
4.
It's 4. So it's going to be what? 4 donated, 4 received. Does that sound about right? Right, it's going to be 4 in total donated, 4 in total received. And as a result of that, how many of each ion do I need? Excellent. You guys been doing your homework. 1 vanadium and 2 oxygens, which makes our chemical formula vanadium oxide VO2. It makes it VO2. So I'm not going to rifle through a bunch of examples when it comes to going from name to chemical formula, because it's just binary ionic compounds. It's the same. The only caveat is that we know the charge on our metal. So I think it's even easier than binary ionic, because you don't even need to think about, for example, what charge calcium has. What charge does calcium have, by the way? So, on Wednesday, like I mentioned previously, I'm not going to be here, so will be a work period. Those are things that, with enough practice, will just become ingrained into your mind. So it's important that you do the practice. I've been pushing you guys pretty hard, to be honest, but we will have a couple work periods coming up, and then we're going to be moving into covalent compounds, which if you are struggling with ionic, covalent's a lot easier, but you need to learn how to do ionic, period. Because later on when we're creating recipes, it's expected that you are able to proficiently go from name to formula and formula to name. It's an essential skill for all of chemistry. Okay, so get to work. If you have questions, let me know.